All right, welcome to today's Explainer. If you're a civil engineering student or honestly just someone fascinated by how we manage to scrape the sky with these massively heavy structures, you are absolutely in for a treat today. We're looking at a huge structural paradigm shift in geotechnical engineering. We're going to explore exactly how the foundations beneath our feet are evolving, specifically diving into a game-changing concept that is literally reshaping how we support the world's tallest buildings.
Let's kick things off with a pretty massive, real-world number. How could a single engineering decision save nearly 3.9 million euros on a skyscraper's foundation? Well, that is exactly what happened with the 256-meter-high Messerturm Tower over in Frankfurt, Germany. By changing just one core philosophical approach to how they designed the concrete beneath the ground, the engineers saved millions, and they did it without compromising a single ounce of safety. Understanding exactly how they pulled this off is absolutely essential for your future careers.
So, to understand that massive saving, we really have to look at this fundamental shift in engineering philosophy. We're moving away from the old paradigm, which is this over-conservative, capacity-based design, to a completely new paradigm, a highly efficient, settlement-based design. You know, the old way just throws a ton of concrete and steel at the problem just to be safe. But the new way, it uses brilliant, calculated mechanics to use exactly what is needed to control how much the building actually settles into the earth.
Here is our roadmap for today's Explainer. We'll start with the high-rise foundation problem, introduce the CPRF concept, dig into the four crucial interactions, break down the load-sharing dynamics, and then finish up with sustainable and economic design.
Okay, Section 1. The high-rise foundation problem. Specifically, outdated design codes. Every good engineering story needs a villain, right? And in our case, it's these overly conservative regulations.
So here's the critical flaw we've been dealing with for decades. When engineers needed to support a really heavy high-rise, they designed a massive concrete raft. Now, if the soil wasn't perfectly stiff, they just add deep piles underneath it. But here is the crazy part. Traditional regulations often force engineers to design those pile groups as if the raft isn't even there. They're forced to totally ignore the raft's load-bearing capacity, meaning the piles are designed to carry 100% of the building's weight. It's wildly redundant and leads to massive, expensive over-conservatism.
Which brings us to Section 2. Enter the CPRF concept, our hybrid foundation. This is the real hero of our explainer, a system that finally forces the raft and the piles to communicate and actually collaborate.
So what is it? A combined pile-raft foundation, or CPRF for short, is a hybrid foundation system combining the load-carrying capabilities of both the raft and piles as a single cohesive unit. Instead of the piles taking all the weight, they essentially act as settlement reducers. They're placed strategically just to keep the building from sinking or tilting too much, while the raft itself actually does a huge amount of the heavy lifting. As you move into your careers, you're generally going to encounter two main flavors of CPRF. On the left here, we have a pile-enhanced raft. This is for when your ground is actually pretty decent. So the raft carries the majority of the design load, and we just add a few piles to fix local weak spots or differential settlement. Then, on the right, we have a raft-enhanced pile system. This is where the piles take the majority of the load, but they're spaced much wider apart than in a traditional group, and the raft is officially calculated into the mix to share the burden. Moving right along to Section 3, the four crucial interactions soil-pile-raft mechanics, it's time to take this explainer underground and visualize the complex, invisible mechanics that make this whole system tick.
You see, when you combine a raft and piles, it's not just simple addition. The soil sandwiched in between them creates a highly complex interaction zone. There are four distinct interactions you have to calculate. First, pile-soil interaction, which is the friction along the pile. Second, pile-pile interaction, basically how one pile's stress affects its neighbor. Third, raft-soil interaction, the contact pressure of that massive concrete slab on the dirt. And fourth, the absolute most vital one, pile-raft interaction. The way the raft pushes down on the soil actually changes how the piles beneath it behave.
Now, the physics of that interaction? Absolutely mind-blowing. Initially, you get this negative interaction, because as the raft pushes the soil down, it actually reduces the relative friction the piles can generate against that soil. But as the building settles further, this shifts into a positive interaction, where the combined stiffness of the soil and piles unlocks the raft's true bearing capacity. And get this, research shows that the piles magically mobilize their full capacity only when the foundation settles to about 1.5 to 2% of the raft's total width. That right there is your operational sweet spot.
Now, obviously, because these superposition effects and stress fields are so incredibly complex, you are not calculating this on the back of a napkin. Geotechnical professionals use advanced discretized three-dimensional finite element models like Plaxis 3D to simulate the CPRF in sand or clay. This software is what helps us visualize those invisible stress webs to prove that the system will hold up under massive vertical loads.
Which brings us to Section 4, Load Sharing Dynamics. We've seen the physics, but how do we mathematically distribute the weight of a skyscraper across all these components?
The absolute most critical variable you need to know for CPRF design is the alpha CPRF coefficient. It's essentially just the specific ratio of the load carried by the piles divided by the total vertical load imposed on the entire foundation. Very simply, it tells you exactly who is doing the heavy lifting. Think of it as a sliding scale. If your alpha CPRF is exactly 0, the piles are doing absolutely nothing. You just have a pure spread raft foundation. On the flip side, if your alpha is exactly 1, the raft is doing nothing and you've got a pure conventional pile group. To actually utilize the CPRF method and have these components truly collaborate, engineering codes specify this coefficient has to sit right in the sweet spot between 0.0 and 0.9.
Compare that to the old way to see how this builds a much better mathematical model. The old method was incredibly simplistic. You're just summing up individual pile capacities independently. The new CPRF method is highly accurate. To find your ultimate limit state, you calculate the capacity using specific interaction multipliers, alpha pre for Pile-Raft, alpha pop for pile-pile, and alpha RP for raft-pile. By factoring in those interactions, your mathematical model suddenly perfectly aligns with physical reality.
And finally, Section 5, Sustainable and Economic Design. We know the math works, but let's look at the real-world professional impact of actually adopting this advanced methodology.
In practice, implementing CPRF takes 3 mandatory stages. Step 1 is the preliminary stage, which is basically a feasibility study to see if the local soil profiles even allow for this setup. Step 2 is the detailed design stage, where you're running those heavy 3D finite element models we just talked about. But step 3 is what makes this truly safe, the observational stage. In the real world, engineers actually install sensors to verify that the settlement models match the physical, real-time sinking of the building during construction. That real-world verification is key.
Okay, remember that massive 3.9 million euro saving we talked about right at the beginning? Here is the visual proof of exactly how they did it for the Mesoterm Tower. A conventional group pile design would have required 316 deep foundation piles. By utilizing the CPRF design and allowing that raft to share the load, they reduced that to just 64 piles. That is nearly an 80% reduction in pile count. Just incredible.
The ripple effects of that are just huge. Economically, fewer piles means millions saved in material and labor. It's incredibly sustainable, slashing concrete and steel usage. It's highly efficient, resulting in significantly faster construction times for the crew. And above all, it remains perfectly safe, providing exceptional, mathematically proven settlement control.
So, I'm going to leave you with a question to think about. As the civil engineers who will literally be building our future skylines, the choice is yours. Are you ready to embrace the complex, highly efficient, and sustainable mechanics of the foundations of tomorrow, or will you stick to the wasteful, conservative codes of yesterday? The math is there, the software is there, and the millions in project savings are right there for the taking. It is entirely up to you to champion this CPRF paradigm shift. Thank you so much for joining me on this explainer. Keep studying hard, and I will see you next time.